Hi everyone, I would like to welcome all of you to today's class. In this class, we are going to discuss about the continuous charge distribution, that is surface charge distribution, volume charge distribution, linear charge distribution. So this is electric charge and electric field part 9. Okay, first let us start with the meaning of the continuous charge distribution. Continuous charge distribution. That means very simple. If a charge that is spreads over a region in a continuous manner, the charge spreads over a region, either it may be one dimensional or two dimensional or three dimensional. If a charge spreads over a region in a continuous manner, that is the meaning of continuous charge distribution. So that is of three very important types. Number one, volume charge distribution. That means if a charge spreads over three-dimensional volume in space, if a charge spreads over three-dimensional volume in space, that is volume charge distribution. If a charge spreads over two-dimensional surface in space, that is surface charge distribution. If a charge spreads over one-dimensional line or curve in space, that is linear or line charge distribution. So this is the continuous charge distribution. Here charge spreads over a region that is in a continuous manner. So now we can choose a very small charge and continuous charge distribution, that is dq. dq is a very small charge and continuous charge distribution. Now let us consider an observation point P. At that point we have to calculate the net force, resultant force acting on a unit positive test charge. Okay, and also we have to calculate the net electric intensity at point P, that is a near continuous charge distribution. So here a unit positive test charge plus Q naught is placed. Due to this small charge plus dq, plus Q naught will experiences repulsive force. So O is the location of plus dq. Due to plus dq, plus Q naught will experiences the repulsive force. So that is df vector. So distance from O to P is r, and r cap is a unit vector, indicates the direction of df vector, that is along OP. So the force acting on plus Q naught due to plus dq plus dq, that can be calculated by using the Coulomb's inverse square law in vector form. According to Coulomb's inverse square law in vector form, the force acting on plus Q naught due to plus dq, so that is df vector is equal to 1 divided by 4 pi epsilon naught. Two charges, one is Q naught and another one is dq, divided by square of the distance from dq to p, that is r. R is the distance from O to P. So divided by r square into r cap. So this is the force acting on plus Q naught due to plus dq. So but we have to calculate the net force, the resultant force acting on plus Q naught, that is due to the entire continuous charge distribution, that can be calculated by using the principle of superposition. According to the principle of superposition, the net force at point P due to the entire continuous charge distribution that is given by the vector sum of forces produced by individual small charges, in continuous charge distribution. So the F vector actually, that is integration of the F vector. F vector is equal to integration of the F vector. So F vector is equal to integration of df vector. So that is 1 divided by 4 pi epsilon naught q naught dq divided by r square and r cap. Okay, now the constant terms, that is taken as outside. So here, what are the constant terms? Q naught is constant, 4 pi epsilon naught is constant, dq is variable, r is variable, even r cap is also variable. So Q naught divided by 4 pi epsilon naught, that is taken as common integration of dq divided by r square into r cap. So this is the mathematical expression for the net force acting on unit positive test charge, that is due to the continuous charge distribution. Net force at point P, that is near the continuous charge distribution. And this formula is very, very important. F vector is equal to Q naught divided by 4 pi epsilon naught integration of dq divided by r square into r cap. So after that, we have to calculate the electric intensity at point P. Electric intensity at point P. So what is the meaning of electric intensity at a point? Electric intensity at a point means the force experienced by electric intensity at a point means the force experienced by a unit positive test charge placed at that point, the point under observation, the point under consideration. Okay, so that can be calculated by using the mathematical expression, that is E vector is equal to, what is the formula? E vector is equal to F vector divided by Q naught. E vector is equal to F vector divided by Q naught. So F vector is Q naught divided by 4 pi epsilon naught integration of dq divided by r square into r cap whole divided by Q naught. So Q naught get cancels. So finally we will get the expression for electric field. E vector, that is equal to 1 divided by 4 pi epsilon naught. E vector is equal to 1 divided by 4 pi epsilon naught integration of dq divided by r square into r cap. So direction of E vector, direction of F vector, both are same, right? So this is the general expression for net force at a point near the continuous charge distribution. Okay, so after that, let us discuss about the first type of the continuous charge distribution, that is volume charge distribution, and this is the first type of the continuous charge distribution. What is that? Volume charge distribution. That means very simple. If a charge that is spreads over three-dimensional volume. If a charge that is spreads over three-dimensional volume, that is in space. Okay, so that is the meaning of volume charge distribution, and that is having a volume charge density. The volume charge density means the charge contained per unit volume. So this is a mathematical expression for volume charge density. So rho is equal to Q divided by V. So this is the mathematical expression for volume charge density. So the SI unit of volume charge density is Coulomb per meter cube. So this is also very important. Charge is measured in terms of coulomb. Volume is measured in terms of meter cube. So coulomb per meter cube. Coulomb per meter cube. That is the SI unit of volume charge density. So what is the meaning of volume charge density at a point? Actually, this is now volume charge distribution, and this is a very small volume, very small volume in volume charge distribution. This is a very small q, and this one having volume is dV, and having charge is dq. Okay. So what is the meaning of volume charge density at a point? That means charge contained per unit volume. Charge contained per unit volume at that point. So this is a mathematical expression. Rho is equal to dq divided by dv. Volume charge density at a point means charge contained per unit volume at that point. So this is volume charge density, simply charge per unit volume. Volume charge density at a point means charge contained per unit volume at that point, the point under observation. Okay, so what is the net force acting on plus Q naught due to the entire volume charge distribution? That can be calculated by using this formula. F factor is equal to Q naught divided by 4 pi epsilon naught integration of dq divided by r square into r cap. So here dq means charge contained in small volume dv. So rho is equal to dq by dv. So what is the value of dq? What is the value of dq? dq is rho into dv. Rho into dv, right? So just we can replace dq by rho into dv. Okay. So this is the mathematical expression for the net force acting on plus Q naught due to the entire volume charge distribution. And the net electric field, that is E vector is equal to F vector divided by Q naught. So instead of dq here, we can write, what is the value? What is the value of dq here? Rho into dv. So this is the expression for the resultant electric intensity at point near the volume charge distribution. Okay. So here one very important special case is there. Suppose if a charge spreads over the entire volume of the sphere, the charge spreads over the entire volume of the sphere, that sphere having the radius is capital R, then what is its volume charge density? So sigma, that is rho is equal to, so the n-type charge is q divided by, so rho is the symbolic representation. Rho is equal to q divided by, so entire volume 4 by 3 pi r cube. So rho is equal to q divided by 4 by 3 pi r cube. And this is the mathematical expression for volume charge density of the sphere. So the mathematical expression for volume charge density of the sphere is rho is equal to q divided by 4 by 3 pi r cube. So this is the first type of continuous charge distribution. Okay. The next one is second type, that is surface. That is surface charge distribution. Surface charge distribution. Surface charge distribution means if a charge that is spreads over two-dimensional surface, that is in space. If a charge that is spreads over two-dimensional surface that is in space, that is the meaning of surface charge distribution, that is having surface charge density, that is having surface charge density. So the surface charge density symbolic representation is sigma. Okay, sigma is equal to Q divided by S. S is surface area. Charge per unit area is surface charge density, and its SI unit. What is the SI unit of surface charge density? Coulomb per meter square. Charge is measured in terms of coulomb. S means area. Area is measured in terms of meter square. Coulomb per meter square. That is the SI unit of surface charge density. So, what is the meaning of surface charge density at a point? So, that is also very important. Surface charge density at a point means charge contained per unit area at that point, the point under observation. So, that is sigma is equal to dq divided by ds. So, now actually this is surface charge distribution. Charge spreads over a two-dimensional surface. Charge spreads over a two-dimensional surface that is in space. Charge that is spreads over a two-dimensional surface in space. And this is the small surface area that is considered, that is ds, and then the charge is dq. Okay, and this is the observation point at this point. Now at this point we have to calculate the net force and net electric intensity that is due to the n-type surface charge distribution, that can be calculated by using these two formula. Okay, so so first one, F factor that is equal to Q naught divided by 4 pi epsilon naught integration of dq. So here, what is the value of dq? Here dq means charge contained in a small area ds. dq means charge contained in small area ds. So that can be calculated by using this formula. Sigma is equal to dq divided by ds. So charge contained in small area ds dq, that is equal to sigma into ds. So instead of dq, here we can write sigma into ds. So this is the mathematical expression for the net force acting on plus Q naught due to the n-type surface charge distribution, and the net electric intensity instead of dq. So here value is sigma into ds. So this is the mathematical expression for net electric intensity at a point due to the n-type surface charge distribution. And then actually surface charge distribution that entirely depends on the shape of the conductor. So for example, let us consider a hollow spherical conductor. So the electrons are removed from the metallic sphere. What happens? The sphere gets positively charged, that is continuously spreads over entire surface area, that is actually surface charge distribution. Okay, now let us consider the radius of the sphere is r, the entire charge on the sphere is q. So then what is its surface charge density? What is the surface charge density of the sphere? Sigma is equal to so entire charge divided by, so surface area is 4 pi r square, that is the surface area of the sphere. So this is the mathematical expression for a surface charge density of the sphere. Okay, so surface charge distribution, that is entirely depends on what? Shape of the conductor. Suppose if the shape of the conductor is uniform, surface charge distribution is also uniform. Suppose if the shape of the conductor is non-uniform, like this, shape of the conductor is non-uniform, the surface charge distribution, that is also non-uniform. Surface charge distribution is also non-uniform. So look at this diagram. Actually here at pointed ends, what happens? At pointed ends, more number of charges are accumulated. Okay. So at pointed ends of the conductor, more number of charges are accumulated. That is due to the repulsion of the same type of charges. Pointed ends of the conductor, more number of charges are accumulated. That is due to the repulsion of same type of charges, and some charges, those are leaked into the surrounding space. Okay, actually that process is called discharging action of sharp point, or simply action of point, or discharging action of sharp points. That means at pointed ends of the conductor, more number of charges are accumulated. That is due to the repulsion of same type of charges, and some charges, those are leaked into the surrounding space. So that is the meaning of discharging action of sharp points. Okay. So how does the surface charge density depends on the curvature? Actually, surface charge density, is directly proportional to curvature. Surface charge density is directly proportional to curvature. So if the curvature is maximum, surface charge density is also maximum. Okay, look at this diagram. The curvature is maximum. Surface charge contained per unit area is also maximum. Surface charge density is also maximum. If the curvature is minimum, surface charge density is also minimum. So how does the surface charge density depends on the curvature? Surface charge density, that is directly proportional to curvature. If the curvature is maximum, surface charge density is maximum. If the curvature is minimum, surface charge density is also minimum. Okay, how does the surface charge density depends on the radius of curvature? Okay, what is the meaning of the radius of curvature? A radius of curvature means that is actually the radius of the sphere. Listen to me carefully. Radius of curvature. Radius of curvature means that is the radius of the sphere, but the given spherical surface, that is the part. Radius of curvature means radius of the sphere, but the given spherical surface is a part. Okay. So if the radius of curvature is gradually increases, what happens to the curvature? Curvature is gradually decreases. The radius of curvature is gradually increases, curvature gradually decreases. That means the radius of curvature is inversely proportional to curvature. The radius of curvature increases, what happens to the curvature? Gradually decreases. Suppose if the radius of curvature is infinity, curvature completely becomes zero. Okay. Now, you can tell me how does the surface charge density depends on the radius of curvature. Surface charge density, that is inversely proportional to radius of curvature, right? Surface charge density is directly proportional to curvature, inversely proportional to radius of curvature. And this is the second type of the continuous charge distribution. So the last one, that is Linear or line, linear, linear or line charge distribution, linear or line charge distribution. So linear or line charge distribution means if a charge spreads over one dimensional line or curve in space. Okay, if a charge spreads over, if a charge that is spreads, charge will spreads over a one dimensional line or curve that is in space. That is the meaning of linear charge distribution, that is having linear charge density. So the mathematical expression for linear charge density, that is lambda, is equal to Q by L, charge per unit length. Charge per unit length is linear charge density. So linear charge density at a point, let us consider one particular point. This is O, and P is the observation point. At that point, we have to calculate the net force and the net electric intensity that is due to the entire linear charge distribution. Now, a unit positive test charge plus Q naught is placed at the observation point T. So, due to a small charge plus dq, then small and dl. So plus Q naught will experiences the repulsive force, that is dF vector. So distance from O to P, this is R, and direction is R cap. R cap is the unit vector, indicates the direction of dF, indicates the direction of dF vector, that is directed from O to P, O to P direction. So what is the meaning of linear charge density at a point? Linear charge density at a point means very simple. The charge contained per unit length, charge contained per unit length at that point, and its SI unit. SI unit of linear charge density. Lambda is a symbolic representation of linear charge density, and its SI unit is coulomb per meter. Coulomb per meter. So the net force acting on plus Q naught due to the entire linear charge distribution. So that is F vector is equal to Q naught divided by 4 pi epsilon naught integration of instead of dq. So now here we can write, that is instead of dq, what is the value? By using this mathematical expression, dq is lambda into dl, lambda into dl, right? So this is the net force acting on plus Q naught due to the entire linear charge distribution. And the electric field, so this is 1 divided by 4 pi epsilon naught integration of dq. dq is lambda into dl divided by r square into r cap. So this is the mathematical expression for electric intensity, net electric intensity at point P due to the entire linear charge distribution. Okay, so let us consider a small ring. It is having radius is capital R. Okay, now the electrons are removed from the ring. What happens? The ring gets positively charged, that is distributed over entire length of the ring. So then what is its linear charge density? That is lambda is equal to entire charge on the ring is q divided by the entire length of the ring, that is circumference. What is that? That is 2 pi r. So this is the mathematical expression for a linear charge density of the ring. Okay, thank you.